Good evening, sir. Hello. Hello.
Teacher,
Hi and good evening, everyone. First of all, are you able to see my screen and hear me? Um, so, are you guys able to see my screen and hear me? Okay, yeah. So we'll just start. So good evening once again and welcome to this problem solving session for this course on fundamentals of power electronics. This will be the week 2 of the solving session, and I presume you have gone through the lecture slides from the professor, and this week you dealt with BJT devices. In particular, you studied about the static and dynamic characteristics. That is, in static characteristics, you kind of learned how to plot the output characteristics, that is the VCE versus IC curve. And then, of course, you went on to the dynamic characteristics, wherein you studied about the switching, right? That is how the device will turn on and turn off. Then, once you studied both the static and dynamic characteristics and understood its operation, you kind of learned how to calculate the losses, right? So you of course know that the loss components, the loss is going to be composed of two components. One will be the component contributed by your conduction loss, or due to the BJT's normal conduction in a switching cycle. Let's say the BJT is on for 80% of the time period or so. So during the 80% of the time period, collector current is going to flow through the BJT, and there would of course be a drop VCE, right? So you multiply both of them, you get the power loss, and that's your kind of the conduction loss, whereas your switching loss is going to be when the device turns on and turns off, right? You might have studied that switching loss is going to be dependent on how much time it takes for the device to turn on or turn off. That is, you have the parameters called T on and T off. So the longer your time period, that is longer your T on or T off, more will be your losses, right? Because your switching energy is going to be higher, therefore your switching losses will also be higher. We will of course see problems on loss calculation, right? And then you came into parallel operation of the device. You understood that since BJT is kind of a minority charge carrier device, right? It has a negative temperature coefficient of resistance, which means that if there is even a slight mismatch, right, then one of the devices is going to carry higher current, right? And this is kind of it will kind of have an avalanche effect, wherein the device that's carrying higher current is going to carry even more higher current, right? Because its effective resistance is going to decrease. So at some point of time, what will happen is this device is going to carry the entire current and it may get damaged. So once this device gets damaged, the entire current will flow through the other device, and hence the other device will also get damaged. So it's going to lead to a catastrophic failure, right? So you studied about that aspect, and finally you came to what is known as a Darlington connection, right? That is, you have a BJT of a certain beta or HFE. How do you increase it, right? So you kind of learned a connection that would actually hand you an effective beta value that's going to be higher than your actual betas, right? So that is what we call the Darlington connection. So we will of course be seeing problems on a majority of these topics today, and we'll just jump right ahead into the problems. If you have any doubts, as usual, you can unmute and ask, or you can write in the comment box. I will check it periodically. Okay. So yeah, so in the last week we completed the diode, right? That is, it's a unidirectional device and unipolar device, right? It can block negative voltage, it cannot block positive voltage, and it can only conduct current from anode to cathode and not the other way around, right? So that's kind of an uncontrolled device. So in this week you learned about BJTs, right? So you of course know that a BJT can carry the collector current, right? And there would be, of course, a drop VCE if you take an NPN BJT, right? So it can block positive voltage as well, because unless you supply the base current required for the device to turn on, the device will not turn on, right? So you get this base as the control variable, right? Base current as the control variable. So you need to inject a sufficient base current in order to make the BJT come out of its cutoff region, right? And of course, you learned about its three regions of operation, that is cutoff region, then you have the active region, and then we have the saturation region, right? So if you want to operate the BJT as a switch, you of course know that okay. So that's about your BJT. Okay. One thing is over here you can understand that it can carry current unidirectionally, right? That is from collector to emitter side, right? Or it can block collector to emitter voltage. What people generally do is they also have an anti-parallel diode connected externally. Okay, something like this. So if you do something like this, you also get the functionality of reverse conduction, right? That is, now current can also flow. Yeah. So current can also flow through this antiparallel diode in the other direction, right? So you also get this particular region of operation, right? Just by adding an antiparallel diode, right? Okay. So this was just an extra piece of information which might be useful in one of the problems. Okay, fine. So we'll just jump right into problems, and of course we have a mix of theoretical and a lot of problems as well, numerical problems. Okay. So capacitive or inductive load when connected to BJT causes abnormal switching transients during dash. Delay time, rise time, storage time, fault time, both rise time and fault time. So okay, so we can make this a little interactive. Does anyone have the solution to this? Can anyone tell the answer? You can type in. For question number 1. So when you connect a capacitive load or an inductive load to a BJT, so what is it going to affect? Will it affect your steady state value or will it affect your transient value? Of course, you can understand that in steady state, the capacitor is going to behave as a okay, so let me go to full screen again. You understand that in steady state and a capacitor behaves as a open circuit, right? Right? And inductor is going to behave as a short. So understand that in steady state, the capacitor or inductor, whatever you connect as a load, it will not have any impact on the operation of the BJT, right? Because it will either be an open circuit or a short circuit. So you just modify your circuit accordingly. But during transients, what's going to happen, right? That is, during transients, what they do mean by transients is you have a particular value of didt, that is didt not equal to 0, and dvdt is not equal to 0, right? So that is what you mean by transients. So the moment you tell that didt is not 0 or dvdt is not 0, it means that there is going to be an LDIDT associated with it, and there's going to be a CDVDT associated with that, right? So of course these are going to come into play. So that's kind of a layman understanding of what's going to happen. So the question is, what would it affect? Will it affect the rise time, fall time, or what? So if you had gone through the dynamic characteristics of BJT, then in one of the lecture slides, you would have understood that the way a BJT turns on, right? So let's say this is your time axis and you have your voltage and current, okay? VCE, okay? So let's say that BJT is going to turn on, right? That is, so the BJT current is almost close to 0. It's not equal to 0. Of course, you know that this current is going to be ICE naught, right? So what will happen when you turn on, let's say you turn on the BJT at this instant, right? At T1, right? So what will happen? Your current would increase, right? And it would go till the actual load current that it's supposed to go to, right? It may be some 5 milliamps or 500 milliamps or 1 amp or 2 amp or whatever it is, but it will rise till your actual load current, right? And then it will remain over here. What about your voltage? Your voltage is actually going to fall from, let's say this voltage was something like VCC, right? It was blocking VCC prior to this, and what will happen? The voltage yeah. So what would happen? Your voltage would kind of fall to a value which is almost zero, but it may not be zero, of course. It would fall to a value to almost zero, right? So let's say this particular instant is T2. Okay. So you understand that this particular time is going to be your on time, right? And similarly, when you want to turn off the diode or when you want to turn off the device, what happens is your current is going to fall to ICE naught and your voltage is going to increase back to VCC, right? So this is what happens during T off, right? So this is your T off. So you understand that during turn on and turn off transients, there is a particular value of dVdt, right? There is a particular value of dIdt, and the roles reverse during turn off, right? Again, there is a di by dt. So that's a positive dIdt, it's a negative dVdt. Again, it's going to be a negative dIdt and it's going to be a positive dVdt. So you understand that during these intervals, that is during turn on and turn off, there is a non-zero value of dIdt and dVdt, and that's actually going to affect your switching transients. In case you have a capacitive and inductive load, what would happen? These capacitive and inductive loads would come into play and they are going to affect your values of dIdt or dVdt, right? So you can understand that during turn on and turn off, capacitive and inductive loads are going to come to play, right? So during the rise time, that is during the current rise time, or you may call it on time as well. So during the current rise time and during the fall time, current fall time, right? So both during rise time and fall time, you see that capacitive and inductive load are going to cause abnormal switching transients. So what you might see is something like, okay, this is kind of an idealized waveform. Just for you guys to kind of appreciate this, what you might be seeing is something like the waveform would be, so the waveform is expected to be something like something like this. And similarly for during turn off as well, you would see some undershoots, and same thing would repeat for the voltage as well, right? You would see something like this. Because of the presence of inductor and capacitor, it's going to have some kind of resonance. It would now be kind of an LCR circuit, so it would then kind of damp out. Okay, fine. Yeah, that's what it would cause, higher order transients, and that's what I just drew right now. Okay. Okay, so we will see a numerical example. An NPN BGT carries a collector current of 200 milliamps. Beta is 100, base resistance is 500 ohms, and VBE is 0.6 volt. What is the value of VBB in volts? Okay, so it's a pretty simple problem. So everything is given over here, right? And since the region of operation is not given, right, you directly assume that your IC is going to be beta times IB, and then you just go ahead and solve, right? So what is given over here? Sorry. So IC is 200 milliamps and beta is 100. RB is 500 ohms and VBE drop is actually 0.6 volt. Okay. So let me use a different link. Right. So what about your IB? Since your IC is given, your IB is going to be IC over beta, right? Because IC is beta times IB. So 200 milli divided by 100 or 2 milliamps is your IB, right? And you apply KVL in this loop, right? In the base to emitter loop. So apply KVL in base emitter loop. What you would end up is with VBB minus IBRB minus VBE is equal to 0, right? So you just substitute over here and you end up with the answer. So VBB is going to be equal to IB times RB, right? That is 2 milli into 500 plus 0.6, right? So your VBB is going to be 0.6 plus 1000 milli or 1, right? So 1.6 volts, right? So just has 2 steps. Okay. Very simple problem. Yeah. Yeah, so the PPTs are getting uploaded in a Google Drive. So yeah, you can access it from the Google Drive. I will share the link of the Google Drive. Okay. So how is a BJT being controlled is more beneficial than a diode? Okay, so in most of the applications you want controllability. Okay, so if you kind of go towards power converters, you will understand its significance. Okay, in most of the applications you want a particular voltage to be blocked, and when you want the device to turn on, only then you want it to turn on. It's not that just because you have a positive voltage you want the device to conduct. Okay, right? In a switch you want controllability, right? You want to control the switch. So that's why BJT being controlled is of course beneficial than a diode. We will see more power converters in later lectures, then you will understand the significance of why controllability is required. Okay. Okay. Yeah, so you get 1.6 volt. So we will go to the next problem. In BJT has HFE beta of 100, base resistance of 500 ohms, load resistance is 30 ohms, VB is 0.6, VBB is 5 volt, and VCC is 10 volt. If the BJT carries collector current of 200 milliamps, what is the value of VCE drop, right? So what is the value of VCE drop in volts? Okay, so the procedure is quite simple again. Just apply KCL, KVL, and you end up with the answer, right? So again, what's given? HFE is 100. Your RB is again 500 ohms. RC, or the load resistance as he calls it, is 30 ohms. VBE is 0.6 volts. VBB is 5 volt and VCC is 10 volts. Okay, so the collector current is 200 milliamps. Okay, so what is the value of VCE? So again, a pretty simple problem. I'm sorry, I'm getting a lot of notifications. Oh, sorry. Yeah, thanks for letting me know. I didn't realize. So for how much time the screen was not visible? 6:24. Okay, for the last 2 minutes only. Yeah, so we were just seeing this problem, right? So HFE is given, RB is given, RC is given, VBE is given, VBB is 5, VCC is 10 volts. So if the BJT carries collector current of 200 milliamps, what is the value of VCE in volts? So he is asking the drop. Okay, fine. So first of all, what you do is you can, once you know what is your IC and once you know what is your beta, you can of course find out what is IB, right? So what's your IB? IB is going to be IC by beta, that is 200 milli divided by 100, right? Again, it's going to be 2 milliamps. Okay. So, and then what is given? He is asking what is VC in volts. Okay. So you of course have two loops here, right? So you have the base to emitter loop and then you have the collector to emitter loop. So apply KVL in both of these regions and then you end up with the answer, right? So we are going a bit slowly, but anyway, yeah. So IB is again 2 milliamps. So I'm just going through this using the solutions because we have a lot of questions to discuss, and I thought we will directly solve some on the screen and some I can just explain with steps. Okay. Yeah. So as I told, you apply KVL in the collector to emitter loop and you apply KVL in the base to emitter loop and you end up with the answer. So over here, VBB is given, right? So in the question, VBB is given, RB is given, you know what is IB, and the VBE drop is also given. So from this, you can compute what is VEE, right? So that is what is being done over here, right? So it is just an application of KVL in the base to emitter loop. Okay, KVL in base to emitter loop. Okay, so you got what is VEE. Once you get what is VEE, you apply KVL in the collector to emitter slide, right? So that is what is again done over here. This is KVL in collector to emitter side. Okay. So what is KVL in collector to emitter side? VCC minus ICRC minus VCE minus VEE equal to 0, right? So from that you can compute what is VCE. Yeah, so I guess now it would be visible again. Yeah, so as I was telling, we apply KVL in the base to emitter loop first, find out what is VEE, right? And then you apply KVL in the collector to emitter loop, right? And from that you can obtain what is your VCE. Okay, right. So that is what was asked in the question. That is to find out what is VCE, right? Okay. So this is again a pretty simple problem. Just we found out what is the base current, apply KVL in base emitter loop, apply KVL in collector emitter loop. Okay, we will move ahead to the next question. Which of the following characteristics are for an ideal switch? So this is something that we answered in the last problem solving session as well. Of course, you understand that the on resistance needs to be 0 and the off resistance needs to be infinite. Okay, so on resistance needs to be 0 as in like no drop in voltage in on state, and off resistance needs to be infinite as in like no leakage current. Okay, so I think this is pretty simple for all of us. Yeah, so these are the characteristics of an ideal device, and of course it can conduct in all four quadrants seamlessly. Okay, bidirectional voltage and bidirectional current. Right. So in the following figure, which should be the maximum value of RB so that BJT operates in the saturation region? Okay, so the BJT parameters are given, that is beta ranges from 10 to 50, VCE sat is given, VBE sat is given, then VCC is given, RC is given, and VB is also given. Okay, so just try to solve this particular problem. Yeah, so I need doubt so far. Screen is now visible. Yeah. So it's an interesting problem. So one thing is they are asking what should be the value of RB so that BJT operates in the saturation region, right? So first of all, we will go back to the basics. You know that the operation of a BJT is going to be something like this, right? I'm just kind of amplifying this particular region for our own ease. So this is for increasing. This is for increasing values of IB, right? And this is VCE versus IC, right? Okay. So this is the characteristic that all of you are aware. But now I will do one thing. I will just take one operating point. Okay. That is, or one particular characteristic curve. Okay. So let's say we have something like this. Okay. So in this particular region, you can understand that. So till this point, right, that is this particular linear region, or this particular region is going to be your saturation region. Okay. So you know that, and let's say you're feeding a current of IB is, let's say, some 1 milliamp, right, for our own understanding, and this is 100 milliamps. Okay, this is your saturation current. So you know that you have fed 1 milliamps constant, right? From a DC source, you are feeding 1 milliamps constantly to the base of the NPN transistor. And in this region, what happens? Your IC is going to constantly increase with VCE, right? So, and you are also aware of the fact that IC is equal to beta times IB. Okay, right? So for a particular value of IB, right, in the saturation region, for a particular value of IB, if you tell that IC is increasing, right, for a particular value of IB, at 1 milliampere only, it is here. At 1 milliampere IB, it is here, right? So then what is changing, right? Your IB is fixed 1 milliamp, but IC is increasing with VC. That means what? your beta is effectively changing. Beta is increasing, right? And finally, at beta max or beta rated, whatever you call it, at that particular region, your saturation current is reached. Okay. So basically what was happening, let's say this particular, this point is 50 milliamps. This point is 25 milliamps and so on. So what was happening? Your IB is fixed at 1 milliamp. If you tell that my IC is 50 milliamp, it means that the corresponding beta over here, is 100. Corresponding beta over here is 50, and corresponding beta is 25. So what's happening? Your beta is increasing. Okay. And you know that when you reach the maximum value of beta, you transition from saturation region to your active region. Correct? So now we will go back to the question. What should be the maximum value of RB so that BJT operates in the saturation region? So in order to make sure that your BJT operates in the saturation region, always operates in the saturation region, from this particular argument, you understand that lesser the value of beta, more is the probability that you are operating in the saturation region. Okay. So in this particular problem, if even though they have told that beta ranges from 10 to 50, you need to consider beta as 10. Okay. Right. Or conversely, you can also tell that for beta is equal to 10, your IB should be so low so that it is the BJT does not go to saturation. Okay, let me write it. For a particular value of particular value of beta, IB should be driven low, sufficiently low, so that the device remains in saturation and does not go to active. Right? So that the device remains in saturation. So the question is, what should be the maximum value of RB? So I need to put a sufficiently high value of RB so that BJT is operating in the saturation region. So from this argument, you understand that you need to consider beta as 10. Okay. And all others are, I guess, fixed. VCE is given, VB is given, VCC is given, RC is given, and VB is given. Okay. So again, we will make use of KVL in the base emitter loop and the collector emitter loop, and then just go ahead and solve. Okay. Fine. So yeah. So apply KVL in the base emitter loop. What do you end up with? So VB is 10, right? So VB is 10 minus 0.8, right? Divided by RB is what you need to find out, right? So that's going to be your IB, right? And what about your IC? IC is going to be beta times this value. Okay. Fine. They have also given VCE. So this is one, and the other point is KVL in the collector emitter loop, right? So IC is equal to VCC minus VCE by RC, right? That is VCC is 100.5 minus VCE is 0.5, right? Divided by RC is 25 ohms. Okay, so this turns out to be 100 so this turns out to be 4 milliamps, right? So IC is 4 milliamps. So you substitute that over here. So you get IC is equal to beta times IB. As I told, beta should be 10. So 10 into 4 remains 40 milliamps. Okay. So you have your IC. I'm sorry. So let me erase this off. So your IB is going to be IC by beta, right? So IC is 4 milliamps divided by beta, as I told, is 10, right? So 0.4 milliamps is for IB, right? So once you know what is your IB from the first expression, you can find out that RB is equal to 10 minus 0.8 by IB. 10 minus 0.8 by IB, that is 9.2 divided by 0.4 milli. Okay, so 92 by 4 becomes 23. Okay. Okay. Yeah. So, yeah, right. 23. Okay. So yeah, that's what. So IC is 100.5 minus 0.5 by 25. And then base current you compute as 0.4 milliamps. Therefore, resistance is I don't know why suddenly it is. Yeah. So 92 by 4 is 23 and 1 by milli is going to be K. So RB that you need to use is 23K. Okay. So that's what. So under saturation region, maximum value of RB occurs when beta is minimum, right? So that is what we made use of. You compute what is IC, you compute what is IB, and from that you compute what is the resistance, and this will be 0.4 milli, right? So this is going to be 23K, not 23 ohm. Okay. So any doubt in this question? This particular question, as I told you, you should consider the lower value of beta to ensure that the device is in the saturation region and does not go to active region. Okay. And that one you can understand by the fact that in saturation region, right? In saturation region, your IB that you drive is going to be the final IB that you drive is going to be more than IC by beta max. Okay. So that's the condition you make use of here. Okay. Yeah. So I think we have spent enough time over here. Okay. So we will go ahead with the next problem. Again, as I told, it's just KVL in the base emitter loop and collect it to emitter loop, and you make use of the current gain formula, right? You just need to know what beta to use. Here, beta is actually variable, right? So beta should be minimum so that the device is in saturation, right? Okay. So for an NPN transistor, which one is true? Base driver source should have sinking capability. So the negative base current should flow. In saturation region, VCE equal to VBE. This is not true. Collector to emitter leakage current flows only when BJT is on. Of course, this is not true. Leakage current flows only when the device is off. So all of the above is not true. A and C are not true. A and B are not true. The answer is actually A. Okay. So the base driver needs to have sinking capability so that negative base current will flow. When will negative base current flow? A negative base current flows when you want to actually, when you are actually turning on and turning off the device, right? So then in that case, during turn off, a particular negative base current will flow, and this is something that I think it's there in the lecture slides. Okay, so BJT is a voltage control device, current control device, of course. BJT is a current controlled current source, right? So it's a current control device because BJT is a current controlled current source. Why? Because you tell that IC is equal to beta IB. So IB controls your IC, right? IB is a controlling parameter and IC is the value or the thing that is going to get controlled. Okay. So you have your, I do it. Okay. So you have your RB over here, and then of course you have a small diode VBE. So you have your emitter terminal, um, base over here, and collector side over here. Okay. So it's a current control current source. Is it a unipolar voltage device? Of course, it's a unipolar voltage device. It cannot block bidirectional voltage, right? This is something we saw earlier as well. Can it carry current in both directions? Normally, no, but generally people do put antiparallel diode. So therefore, it can of course carry current in the other direction as well, bipolar charge carrier device. And it's a negative temperature coefficient device, right? Because it's a minority carrier device, like IGBT, right? So it has a negative temperature coefficient. Okay. So yeah. So the gain of an NPN transistor is 45. A 10 ohm resistor connected in series with the collector terminal dissipates 2.5 watts of power. Okay. So the base current required to drive the transistor is dash. So we are going into the loss part, that is beta is given as 45, RC is 10 ohms, and he tells that through this resistor a power of 2.5 watt is getting dissipated. What is IB? It's a pretty simple problem, right? So what is the power loss through a transistor or through a resistor? I square R, right? In this case, it's in the collector side, so it's going to be IC square RC. This is the power loss. Okay. So if this is the case, you know what is P, you know what is RC, you find out what is IC. IC is going to be root over, IC is going to be root over P by RC, right? So this is going to be root over 2.5 divided by 10 or root over 0.25, or IC is going to be 0.5, 0.5 amps. Okay, so this is your IC. So you know that IB is IC by beta. Therefore, 0.5 by 45, right? So what is 0.5 by 45? going to be 0.0111. Okay. Yeah. It's a pretty simple problem again. Yeah. So 11 milliamps. Fine. Okay. So referring to question number 2, the transistor emitter is grounded and collector resistance of 10 ohms is connected to 15 volt DC supply. Okay. So VCC is 15. VCC equal to 15 volts. And what is the conduction loss in the transistor? So first of all, what is the conduction loss of the transistor? That is, there is going to be a definite VCE drop. So loss is going to be VCE multiplied by IC. Okay, loss is going to be VCE into IC. Okay, so this is the conduction loss of the transistor. We need to find out what is VCE, multiply with IC, you get the answer. So we will go back to question number 2 to find out the parameters. Question number 2 was here. Yeah. We found out that IC is 200 milliamps, okay. IB is 2 milliamps, and yeah, just I think this is enough. IC is 200 milliamps. Sorry. So IC is 200 milliamps. Okay. IC is 200 milliamps, and so you apply KVL over here to find out VCE. VCE is going to be VCC minus ICRC minus, okay, of course it's going to be zeros. Yeah, VCC minus ICRC, that's going to be 15 minus 0.2 into RC is 10 ohms, right? So 10 into 0.2 is 2, so 15 minus 2 is 13 volt. So what is the power loss? Power loss is going to be 13 into 200 milli, okay, or 2600 milli or 2.6 watts. Okay, so this is the power loss. Simple, right? So you just multiply VCE into IC and you get the answer. Okay, right. So or did we do any mistake? Voltage appearing is C minus ICRC. So IC was 200 or IC was, yeah, in question number 2 IC is given as 200 milliamps. So here I think there is a mistake. It is not, IC is not 500 milliamps, it is 200 milliamps. Okay, should be 0.2. Therefore, it will be 13 volt, and this will be 13 into 0.2, it's 2.6 watt. So they have considered IC as 0.5, it's actually 0.2 in question number 2. Okay. Fine. So till this point, you guys have any doubts, or we can go ahead? Is my screen visible to you? I think we missed 2 questions from start due to screen was not visible. Can you explain again? Okay, so right now we have a lot of questions remaining, so we'll just march ahead. But anyway, we will come back to that. Okay, so So how IC is in milliamps? Yeah, so IC can be in milliamps if it's a signal level BJT. So it may be even around 500 milliamps, 200 milliamps. They are all common values. So question number 5. What should be the maximum value? Okay. So I just explained the gist once again. The point is that we assume that for the device to operate in the, of course, you understand that for the device to operate in the saturation region, for a particular value of IB, you know that since IC equal to beta times IB, you know that you need to ensure, or you will observe that the beta value is lesser and lesser for lesser values of IC. The question is that you want to put a sufficiently high value of RB so that my IB is also minimum and ensure that the device is in saturation region. So in saturation region, you saw that this is the case, right? If you want to ensure that the device is in saturation, you see that the beta value is lesser, right? If you make the beta value lesser and lesser, the device goes more and more into saturation region. Okay, so that's why we have considered the lower value of beta. And then the procedure remains same, right? You just do IC equal to beta times IB, then apply KVL in the base loop and collector loop, and you're done. Okay, so we will just I'll just have water. So give me just 2 minutes, and then we will go ahead. So we still have a lot of problems remaining. Yeah. Yeah, hi once again. Yeah, so the PPTs are already uploaded. I will just, yeah. So 1 and 2 number of question is repeated, explain, repeated again. Okay. Okay, so this is kind of an important problem or kind of a lengthy problem. So we'll just go through it slowly. Okay, so this is regarding the dynamic characteristics. That's something you might have gone through in the lecture slides as well. So the VCE sat is given, that is the on-state drop across the BJT. IC is given, ICO or the collector current with your base open, that is also given some 100 microamperes. Then your VCC is given, right? And then your rise time is given, fall time is given, and the total on period, right? T on is given, and the operating frequency is 10 kilohertz. So if you tell operating frequency is 10 kilohertz, what is the switching period? TS is going to be 1 by 10K, or it's going to be 100 microseconds, right? Find the total power loss in the device. Power loss is how much? So power loss is a summation of conduction loss plus switching loss, right? This is something you guys already know. Okay, so we will find out individually the conduction loss, individually the switching loss, and then just sum them up. Okay, fine. So let's find out the conduction loss first. Okay. So when would the conduction loss happen? When the BJT is on, that is during T on, right? So T on was given as 50 microseconds. So during this period, there is going to be a conduction loss, right? So what's happening during T on? The BJT is in on state. So VCE that they have given is 0.2 volts. And what about your IC? IC is 5 amperes. IC is 5 amperes. Okay. Right. And remember that during the off state as well, right? That is when the device is turned off. So if you know that T on is 50 microseconds, right? So what is your T off? Your T off period is going to be total time period minus T on. Not only this, you also need to remove your rise time and fall time, right? That is minus TR minus TF. Okay. How much is this? TS is 100. So 100 micro minus 50 minus I minus 10, right? So 50 minus 15, that is 35 microseconds. So during this 35 microseconds, your VCE is going to be equal to VCC. That is, the device is going to block entire VCC of 9 volts. And your ICE naught is going to be how much? ICE naught is 100 microamps. So this will again cause a loss, right? So these are the two loss components of conduction loss, right? When the device is completely turned on and when the device is completely turned off. Okay. Also, anyway, during when the device is completely turned off, the loss is going to be very small, right? Because ICE is already 100 micro. So it will be very small, but nonetheless, these constitute your conduction loss, right? So what about your switching loss components? You know that during the rise time, your VCE goes from what to what? VCE goes from VCC to VCE set. Okay. And your IC goes from ICE naught to whatever is your capital IC. Okay. What happens during fault time? Reverse happens, right? That is VCE goes from VCE set to VCC, and IC goes IC to ICE naught. Okay, so I was just talking about what happens during switching loss and conduction loss, right? So you know the conduction loss has two components, that is during turn on, during the entire on period, and during the entire off period. And switching loss also has two components, that is when the device is turning on rise time and when the device is turning off on the fault time. Okay, so I will take the help of a graph over here. So you see over here, so this is during what? This is during TR, right? And this is during TF. So what's happening during TR? During TR, your VCA is going from VCC to VCE set, and IC is going from ICE naught to capital IC. So during TF, reverse happens, right? VCE and IC, they will get just reversed. I'm not writing it again, but it will get reversed. So during this short period of time, that is during TR and TF, there is an overlap of voltage and current. If you tell that there is an overlap of voltage and current, there is always going to be loss associated with it. Okay, and that is what constitutes your switching loss. Okay, so you got two losses, that is conduction loss and loss, and just a second. Yeah. Okay. So as I told, P loss is conduction loss plus switching loss. Okay. So what about conduction? Okay. So I will not explain from here, of course. Okay. So as I was telling, during conduction loss, for conduction loss, we take the entire on period and the off period. So what happens during on period? Your VCE is 0.2 and IC is 5, right? So, and it happens every time when the device is on in the switching cycle, right? So what happens during switching? So what if you observe the switching cycle, or if you observe the IB pulses, right? What about your IB pulses? Your IB will be on for some time, then it will be off for some time. This is, let's say, this is your TS, and the same cycle repeats. And same cycle repeats. Okay, so this is your entire on period, this is your entire off period, and you have TR and you have TF. Okay. So we have to find out the loss components in each of these, right? So okay. So we will just find out the on losses. So when the device is completely on, right? So you know that your VCE is 0.2 and IC is 5. And it is happening for 50 microsecond in a 100 microsecond interval. So what is your energy? Energy loss component? Energy loss component will be directly V into I, right? Because during this period, what is your IB? What is your VCE? VCE is fixed at 0.2. It is fixed, right? It's not changing. IC is fixed at 5 amperes. Okay. So your energy loss component is going to be VCE into IC into how much time it is happening for T on period it is happening. Okay. So this is your energy loss. So you'll find out how much microjoules it is. So it will be what? It will be 0.2 into 5 into T on 0.5 0.2 into 5 into 0.2 into 5 into 50 micro, right? So 0.2 into 5 is 1 into 50. So it's going to be 50 microjoules, right? So this is your energy loss during the on time. So what is the energy loss during off time? Energy loss during off time is going to be your VCC because it was VCC. So VCC into ICE not because right now the corrector current will be ICE not and it will be blocking VCC into E off, right? So VCE is 9 volt and IC not is 100 micro into 35. Nine volt into 100 micro into 35 micro, right? It's very small, right? So 900 micro into 35. How much is it? 900 into 35. Yeah, so it's very small. That is 0.0315 microjoules. Okay, it's in some nanojoules. Okay, we need not worry about it too much. But anyway, yeah. So this is the energy loss during on and off time. So this is the conduction energy loss, right? So this happens in every cycle. So what is the power loss or the conduction power loss? Conduction power loss will be the summation of this multiplied by frequency, right? So 50 plus 0.0315 microjoules into the frequency, right? So what is power loss? Power loss is basically energy times frequency, right? Or E by T, right? E by T. So energy into frequency. Frequency is 10 kilohertz. Okay. How much is it? 50.0315 micro into 10K. It's going to be 500.315 milliwatt. Okay. So it will be 500.315 milliwatt, right? So this is your conduction loss component. We will find out what is your switching loss component, right? So switching loss can be due to TR and TF. So during TR, VCE is increasing from VCC to VCE. IC IC increases from ICE not to IC, something like this, right? And at the same time, VCE decreases from VCC to VCE, right? So this is what happens during TR. So we need to find out the energy loss during this period as well. So finding out the energy loss is a bit different over here. Okay. Why? Because if you tell that your voltage is falling from VCC to VCE sat, and you tell that your current is increasing from ICE not to ICE not to IC. So how can you write your voltage? VCE can be written as, you just need to write a line equation for this. You just need to write line equation for voltage. Okay. So how do you write it? So the initial point, let's say this is t equal to 0 and this is t equal to tr. Okay. So this particular point will be 0 comma VCC. This particular point will be tr comma IC, and this particular point will be 0 comma IC naught, and this will be tr comma VCE sat. From this you can write what is the voltage expression or line equation. So what is line equation? Y minus y1 or y minus y2 by y minus y2 by y1 minus y2 is equal to x minus x2 by x1 minus x2, right? So for voltage, you understand that VCE minus VCE sat divided by VCC minus VCE sat is equal to x minus x1 x2 by x1 minus x2, right? So T minus TR divided by 0 minus TR. So you solve it and then you get what is your VCE. Okay. Similarly, you solve and you get what is IC, right? I'm just telling you the procedure how to do it. Okay. So you get what is VCE, you get what is IC, right? Once you get what is VCE and IC, you know that your power or instantaneous power will be VCE of T multiplied by IC of T. Got it right? We just wrote the line equation. You find out what is your instantaneous power, right? VCE of T into IC of T. That's your instantaneous power. Okay. So you get what is your instantaneous power, and then what you can do, if you integrate your instantaneous power, you find out the area under the curve, right? That is your energy. Okay. You integrate it, you get the energy, and then you multiply your energy into frequency, you get what is your power loss. Okay, that is your capital. You understood this procedure, right? Just give me a thumbs up if you have understood this procedure. What we did was we took the line equation, take the line equation of VCE, take the line equation of IC, multiply both of them, you get the instantaneous power profile. Then find out the area under the curve, that is integrating it, right? You integrate it between 0 to TR, right? You integrate between 0 to TR, you get what is the energy, and multiply that by frequency, you get the power. So did you get it? Why VCC is high and VCE sat is low? So it is typical, right? Because VCC will be some 10 volts or 15 volts or whatever it is. VCE sat will be very small. It's on straight pop. Okay, right. So this is the procedure that theoretically needs to be followed. Okay. Okay. So now for practical purposes, just for you guys to find out the loss in exam, right? It's not easy for you to do this entire thing. It's like a 5-mark question that you are doing, right? You don't want to do it in the exam. So it'll just provide you some empirical shortcuts that you can adopt over here. So we'll go back to basic math. Let's say you have two curves. Let's say I call it x1 of t. x1 of t is something like this, DC value, and x2 of t, again a DC value. Okay. In that case, if you multiply both of them, again you are going to get a constant, obviously, right? And let's say this is for a time period Ts. Okay. So if we do the same thing, that is, this is your voltage, let's say, let me call it voltage, and let me call this as current. And the instantaneous power loss profile will be something like this, right? It will be a constant. So if you have to find out the energy, what will be the energy? V into I, that is what you multiplied instantaneous value. So it will be capital V, that is your absolute value, capital I, V into I, into whatever is your time period, whatever is your T. Let me call this small t. Okay. So this will be the energy, right? V into I into T. Correct. Now let's say my voltage is something like this, and I multiply with the current being something like this. Okay. In that case, you can understand that the multiplication would be something like this, right? This will be Ts. So what you get kind of a triangle, right? So what is the area of a triangle? Half into base into height. So this is your V, this is your I. Okay. So half into base into height. And this is conversely true as well. If this is constant and your I is increasing, you get something like this. Okay. Your voltage may increase or decrease or whatever. Now we will come to our case. One of this is increasing, the other is decreasing. This is what we are seeing, right? This is our case. If you solve the line equation, what you may get is you need to multiply the instantaneous value. So you will be getting something like this. Okay. It turns out that you will get the formula to be something like 1 by 6 V into I into T. Okay. So this is simple, right? This is just a square area of a square. This is just a triangle area of a triangle, half base into height. Over here, you are having two profiles of voltage and current, which are having kind of a triangular shape. One is increasing, the other is decreasing. If you find If you do the line equation and then you multiply both of them, then you integrate it, you will end up with 1 by 6 into V into I into T. Okay. One assumption, note that one assumption is the initial value is 0. Actually, the initial value is not 0, but still over here to derive these formulae, we assume that the initial value is 0. Okay. So did you guys get this? 1 by 6 into V into I into T. You can just give a thumbs up if you got it. I'm telling this formula only for you guys to solve faster. The actual thing is, of course, you need to find out the line equation, then you multiply both of them to get the instantaneous power, then you find out the area under it by integrating. The area multiplied by your switching frequency or the area divided by your switching time period will give you the actual power loss, and that will be the accurate value. But right now, it would not be feasible for you to do that every time. That's why I'm giving you this, right? This is just simple math. Okay, so these are these kind of questions we have solved in class 11 and class 12. Okay, just this is just an integration problem. Okay, we are just making use of that. Okay, so now we will go back to our original thing. So let me add a new slide. So what are we telling? During TR, we are telling that your voltage increases from, or your current increases from ICE naught to IC. However, for using this formula, we assume that, okay, ICE naught is very small, that it is almost 0. And same thing applies for VCC as well. VCC, from VCC, it goes to a value which is almost 0. Okay. So then the instantaneous energy loss during your on time or during your rise time is going to be 1 by 6 into VCC into IC into TR. Similarly, during TF, it's going to be, it is going to be 1 by 6 into VCC into IC into TF, right? So this is during turn on and this is during turn off, right? So if you sum this up, total switching energy will be what? 1 by 6 VCC IC into TR plus TF, right? This is the total switching energy, correct? So 1 by 6 into what is VCC? Your VCC is 9. 1 by 6 into 9 into IC is 5. Right. IC is 5 into TR plus TF. What is? Yeah. So 1 by 6 into 9 into TR plus TF. What is TR and TF? 5 micro and 10 micro. So what does it turn out to be? So yeah, so 112.5 microjoules. So what will be the power loss? Switching loss, as we call it. Switching loss is going to be energy multiplied by frequency, right? So 112.5 micro into 10 kilohertz. Okay. So how much will it turn out to be? 1125 milli, right? Or 1125 milliwatts. So what will be the total power loss? Total power loss will be this plus this, right? Conduction loss plus switching loss. Conduction loss we earlier turned out to be 500, and right now it turns out to be 1.125, right? So your loss is going to be, your total loss will be that plus this, right? So 1.125 plus 0.5. So somewhere around you are going to end up with 1.625 watts. Somewhere around this, right? Yeah, so your conduction loss turned out to be 500 watts almost. I mean 500 milliwatts. And yeah, so we got 1.625, and if you calculate by the original method that I was just telling, using the line equation, right? IC into T by TR, right? That is, if you take the time component in terms of the line and then you integrate it. I mean, anyway, the slides will be available, but anyway, you integrate it from 0 to TR and then you just calculate by the accurate method, you end up with how much? 1.675. So there is a difference of 0.05 watts, but that's fine, right? Around 50 milliwatts difference is there because we have approximated that the lower value of 0. Okay, so till this point, any doubt is there in this particular question? We have discussed this question for the past around half an hour, but still, if you guys have any doubts, please do go ahead and ask. You can always see the other questions. Others are just KVL, KCL kind of questions, but this particular question I thought was really important. Okay. Um, just give me a moment. I'll just have some water. Yeah, so what is 10K in switching loss? So 10K, see, we found out the switching energy, right? That is, switching energy is in joules, microjoules. Okay. So how do you convert joules to watts, right? That is, what is energy? Energy is watt hour, right? That is watt into time. It's your energy. Okay. That is, energy is watt into time. Okay. So what about your watt? uh, that is your power loss. Power loss will be energy by time, right? Loss is equal to energy by time or energy into frequency, right? Energy into frequency is your power loss. So the frequency is given in the problem as 10 kilohertz. That is why I have taken 10K. Got it? So that is why we are multiplying everywhere with 10K. Okay. Okay, so we'll just move ahead. Right. So what is the junction temperature for the power loss found in question 10 if the ambient temperature is 40 and theta is 95 degrees per watt? So I guess this is pretty simple. That is, you do know from the temperature profile that EJ, EJ is equal to TA plus or theta into power loss, right? So TA is 40 or theta is 95 and power loss is 1.675, right? So 1.75. So just do it and you get what is the temperature, right? So 95 into 1.675. Yeah, so it's going to be almost 199.125 degree. Okay. Right. So we will move ahead to the next question. Which region is characterized by the condition IB more than IC by beta, and what is this region referred to as? We just did one of the previous questions based on this condition, right? That is IB is more than IC by beta. That is you're pushing enough IB, right? You're pushing enough IB, but your beta, where are you now? So you're pushing enough IB. Let's say we take this particular operation, right? So you have your IB over here and you have the linear region perhaps till this point. So what happens in this particular region, that is in the saturation region, we told that your beta value is lesser for the same IB. That is what will yield you IC, right? That is IC is equal to beta IB, you know that. So you know that for lesser value of IC, your beta needs to be lesser. Beta effective needs to be lesser. Okay. So your IB can be written as IC by beta. Okay. So in this particular region, in these regions, your IC value is lesser. So your IC by beta is also lesser, right? So your IC is lesser in this region. IC is lesser, IC by beta is also lesser, and therefore your IB is actually greater than IC by beta. In which region? In the saturation region. Okay. Right. So the option is characterized by the condition IB more than IC by beta. It is one saturation region. Okay. High frequency operation of any device is limited by what? Forward voltage rating? No. Switching losses? Yes, we just saw it, right? Because switching losses are going to be 1 by 6 VCC IC into TR plus TF, right? So this is your energy into frequency. That will give you the power loss, switching power loss. Okay. So as you go for higher and higher frequency, as frequency increases, you know that the loss is also going to increase. Okay, so high frequency operation is limited by the switching loss. You can't just go increasing the switching frequency, right? Okay, so we will go to another kind of or another type of problem. What's the okay? Yeah, we still have 15 minutes time. Transistors Q1 and Q2 shown in the figure are identical. Each of them have a DC current gain of beta equal to 100. Find out the voltage V naught. Yeah, so this is again a pretty simple problem. You just need to apply the known principles and just solve. Okay, so apply KVL in this loop, that is the base loop, right? So V in minus IB into 500K minus 0.7 minus 0.7 equal to 0, right? So you find out IB from this. What is IB? IB would be Hmm. 5 minus 1.4 divided by 500. And 0.072 milliamps, right? So this is your IB. Therefore, your IC is going to be, or I should call it as IC1, right? Your IC1 is going to be beta times IB, that is 100 times IB1, right? 100 into IB1. So it's going to be 0.72 milliamps. That's your IC. So what is your IE1? IE1 is going to be IB1 plus IC1. Right? 0.7272 milliamps. You observe over here that oh, so you observe over here that IE1, right? That is the emitter current of Q1 is actually going to the base of Q2. Okay. So IE1 is equal to IB2. Okay. This is what is going as the base current of Q2. So if this is the base current of Q2, your IC2 is going to be what? Beta times IB2 or beta times IE1. Okay. So IE1 is 0.7272 and into 100 is going to be 72.72 milliamps. So it's going to be 72.72 milliamps. So that's your IC2. Okay. So this is your IC2. So you know what is IC2? From that you can find out what is V naught, right? So I'll just go to solutions because we are short of time a little, right? So we found out what is IB1, then we found out what is IE1. We know that IE1 acts as base current for Q2. We found out what is IC2. Once we find what is IC2, we can find out what is V naught, right? That is VCC minus whatever is the current flowing through the 100 ohm resistor. What is the current flowing through 100 ohm resistor? It is the summation of the collector current for Q1 and Q2. Okay, so that is why VCC minus of IC1 plus IC2 into 100. Okay, so any doubt over here? This particular problem? I'll just show that. Right. So V naught will be VCC minus IC1 plus IC2 into 100. Why? Because you need to find out what is the current flowing through here. This current will be just applying KCL IC1 plus IC2. That is the current flowing through 100 ohm resistor. Okay. Right. So choose the correct statement. A transistor will remain on as long as the base current is applied. True. This is correct. A transistor remains on after a high to low pulse is applied. No. A transistor will remain on as long as the collector current is applied. No. Transistor remains on after a high to low pulse is applied. Okay. So the correct answer is this. Because your IC will flow corresponding to what you apply at the base, right? Beta times AB. Okay. Right. So, okay. So this is a diode question. Even after the forward current reduces to zero, a practical diode continues to conduct in the reverse direction for a while due to what? Due to reverse recovery, right? Due to stored charges in the depletion region. That is what causes the reverse recovery, and that's why you get this PRR, IRR, and stuff. Okay. So figure shows a connection of two BJTs Q1 and Q2. Will this connection work under practical conditions? Why? So will this work? Of course, a direct parallel connection of two BJTs will never work, right? The two practical BJTs. Why? Because of the negative temperature coefficient of BJTs, because they are minority charge carriers, they have a negative temperature coefficient, right? So one of the collector emitter resistances will reduce, therefore more current will flow through that. It will reduce even further, resistance reduces even further, more and more current will flow through one of the BJTs. It will get damaged, and hence the other one will also get damaged. So you just cannot parallel two BJTs. Two transistors are connected as Darlington pairs. Current gain for Q1 is 20, Q2 is 25. What will be the current gain of the combined Darlington pair? I presume that you guys had gone through the lecture slides. So what happens in Darlington pair is beta effective is going to get multiplied, right? So you get 20 into 25 and you're going to get 500 as the effective value. Okay. Yeah. So this is what happens in a Darlington pair. Okay. So in the circuit given below, it is given that beta tends to infinity and VBE is 0.7 volt. Find Vx in volts. So this is a very simple problem and it assumes that there is an ideal transistor, ideal BJT. That's why the beta tends to 100 VBE, but VBE is anyway 0.7. 0.7 volts. Okay. So just apply KVL in this loop. What you get is what you get is 0 minus 0.7 minus or plus 2 divided by 1K is equal to your IE, right? So your IE current is equal to milliamps. Okay. So since it is given that beta tends to infinity, right? Beta tends to infinity. You of course know that IC equal to beta times IB, right? Or IE is equal to IE is equal to IC plus IB, right? So IC plus IB can be written as IC by beta. Okay. So since beta tends to infinity, IC by beta is almost zero. Therefore, IE is almost equal to IC. If you tell that beta tends to infinity. Okay. So IC and IE are almost same. Therefore, since IE is 1.3 milliamp, IC is also equal to 1.3 milliamp. Okay. Now you know what is your IC, you know what is IE, you can find out what is Vx, right? So what is Vx? Vx is 10 minus 5k into IC. IC is 1.3 milli minus 1k into 1.3 milli plus 2, right? Just KVL, right? So how much does it turn out to be? 5 into 1.3. 1.3. Right. So 12 minus 1.8. Yeah, so it's around 4.2 volts. Okay, just KVL over here, and since beta is infinity, it means that the BJT doesn't require any current to get biased, any base current to get biased. It's like an infinitesimally small IB is enough to actually turn on your BJT. That's the meaning of beta tends to infinity. Your IB is actually zero. Yeah, so as we calculated, Vx is 4.2 volts. So we are almost time. I'll just see two more questions. When reverse breakdown occurs in a diode, what happens when reverse breakdown occurs in a diode? That is, you are in the third region, right? This is your voltage and this is your current. So normally you see something like this. But when reverse breakdown occurs, you see something like this, right? So yeah, so what happens when reverse breakdown occurs? Your current increases and voltage is almost constant, right? Voltage is almost constant, whereas current goes on increasing. Okay, so this will be the final question for the day. From the datasheet of NPN transistor, find the following: 2N3903. So 2N3903. Find the following: VCE naught, maximum conductor current, current gain, and thermal resistance. Okay. So what is the VCE naught? It is given here itself. VCE naught is 40 VDC. Okay. You can see the highlighted part in my screen. VCE naught is 40 volts. And what is the maximum collector continuous current? Collector current continuous is 200 milliamps. Okay, it will be given the maximum rating tab. Okay, and your thermal resistance is asked. That is, what thermal resistance is it mentioned? Junction to ambient thermal resistance is 200 degree per watt. Okay, fine. And what else is asked? Collector gain at current gain at collector current of 1 milliamperes. So typically your beta is given. So at collector current of 1 milliamp, that is IC of 1 milliamp, right? At IC of 1 milliamp, your 3903 has 3903 has 35. So this is your beta value. Okay, at collector current of 1 milliamp. We just saw previously that as collector current varies, your beta will also vary. You can see over here as collector current varies, your beta is also varying. Okay. Yeah. So this is what we just found out. Right. Um, so it's almost time. I guess we can conclude over here. Okay, so why 2 times 0.7? So I guess this was the question regarding Darlington pair. You go over here, you see in this loop that the loop is something like this, right? That is, it goes like this, then one transistor 0.7, then again you go to the base of Q2 and emitter of Q2. Again, there's a 0.7, right? Here and here. Okay, so that's why I have written 2 times 0.7 in this KVL loop. It's just KVL in the base loop. Just that there are two base emitters coming in the same loop over here. Okay. So yeah, thank you very much. We will just conclude for the day. It's around 8. We have discussed most of the questions. So thank you very much. I'm sorry, I guess my camera got turned off. So thank you very much, guys, for attending. And yeah, thank you. Take care. I will upload the slides um, in the drive link itself. Are you guys able to see the drive link? Or do you want me to paste that drive link over here? Yeah. So yeah, so then we will break for the day. Yeah, thanks. Yeah, I will see that. So we will break for the day today. Thanks very much for attending. Yeah, so the slides are uploaded in the drive. I will, okay, just hang on a minute. I will just give you the drive link. I will just give the drive link in this chat box. So it'll be easy for you. Just hang on a minute. Yeah, so this is the drive link. You can go over here and see. Here the sessions are the PPTs of all the teaching assistants will be uploaded. So under my name, you can go and see if you want to see my slides. You can see other slides, and even the YouTube session links will be here because the sessions will be uploaded in YouTube. Yeah, so if there is nothing, oh, I'm sorry, my mic was probably muted. So of course, yeah, like you should not be doing that from ChatGPT because 25% is for assignment, 75% is for the exam, right? You need to go and do it by yourself in the exam. ChatGPT will not do your exam. So it would be better if you do it by yourself. All of these questions are very simple actually, right? It's just some KCL, KVL, and you just need to know a little bit concept and that's it. Okay, so it's not that big a deal to solve. it's taking this much time for us because we are solving it live, but once you get the hang of it, it's pretty simple. So yeah, don't do from ChatGPT at least. Okay, so then we will conclude for the day. Thanks everyone for attending and have a great week ahead. Bye.